After the renewed interest in studying curves in the 17th century, different mathematicians came up with different methods to find different properties of different curves. But then came Isaac Newton and Gottfried Leibniz, who independently discovered one method to find almost all properties of almost all curves. And this method came to be known as calculus. But in developing calculus, Newton and Leibniz built upon the methods that came before them. And therefore, to better understand calculus and its evolution, it helps to understand some of those earlier methods, particularly the ones that were concerned with finding areas and volumes, and the ones that were concerned with finding tangents. In this video, I'll talk about the pre-calculus methods in finding areas and volumes, and in the next video, I'll talk about the pre-calculus methods of finding tangents. And a good starting point would be in 1615, when Johannes Kepler, who was already an established astronomer, published his book, New Solid Geometry of Wine Barrels, in which he calculated volumes of different shapes and wine barrels. This book could be considered a good starting point for modern calculus because in it, Kepler broke a 2,000-year-old taboo, the use of infinitesimals, which were essential in the early stages of calculus. We saw earlier in the series how the ancient Greek mathematicians considered the use of infinitesimals an intellectual taboo that could lead to errors. And this taboo wasn't challenged much for nearly 2,000 years. But Kepler lived during the scientific revolution, a time when many old beliefs were being challenged and discarded, paving the way for new ideas to flourish. And among these old beliefs that Kepler thought was worth challenging was the taboo around the use of infinitesimals as he recognized their practical value. See, to estimate the volume of a barrel, Kepler divided it into cylinders, found the volume of each cylinder, and then summed them up, or what we call today integrated them. He reasoned that the thinner the cylinders, the more accurate the estimate would be, and that at an infinitely thin cylinders, or infinitesimals, the estimate would be perfectly accurate. Kepler used infinitesimals not only to find the volume of barrels, but also to find the volume of several shapes known as solids of revolution. These are solids that are formed by taking two-dimensional figures, like a circle, ellipse, and parabola, shifting them off different axes, and then revolving them. The book was widely read, and expectedly vigorously criticized for its use of infinitesimals. But despite all the criticism, the genie of infinitesimals was out of the bottle, enchanting many young mathematicians with its power and practicality. And among these young mathematicians was Bonaventura Cavalieri, who took the concept of infinitesimals to the next level with his method of indivisibles, the third method on our list in the history of evolution of calculus. Cavalieri imagined that two-dimensional figures like a square were made up of indefinite number of parallel lines, or in his own words, like cloth woven of parallel threads. And he imagined that three-dimensional figures, like a cube, were made up of indefinite number of parallel planes, or in his own words, like books composed of parallel sheets. Cavalieri called these lines and planes indivisibles, and his main idea was to find ways to sum the indivisibles of various shapes. You may be wondering, what is the difference between Kepler's infinitesimals and Cavalieri's indivisibles? They seem very similar, and they are. However, there's a key difference. See, Kepler imagined his infinitesimals to be of the same dimension as the parent figure, while Cavalieri imagined his indivisibles to be of one dimension less than the parent figure. So for Kepler, a two-dimensional figure consisted of two-dimensional infinitesimals, while a three-dimensional one consisted of three-dimensional infinitesimals. In contrast, for Cavalieri, as we just saw, the indivisibles of a two-dimensional figure are one-dimensional, and those of a three-dimensional figure are two-dimensional. This gave Cavalieri a more systematic way of summing the indivisibles of various shapes. He began with a triangle with a height and base of the same length. Let's call them A. And he set out to find the sum of its indivisibles. So if we call the length of the first indivisible x1, the length of the second indivisible x2, and so on, he simply wanted to add the length of these indivisibles. In modern terms, we write this expression as sigma x, or the sum of x. Now this is a straightforward problem. Since the indivisibles span the entire triangle, then their sum corresponds to the area of the triangle, which is half the base times the height. And since we assigned the value a to both, Cavalieri arrived at the result that the sum of the indivisibles of a triangle with a height and base a is equal to a squared over 2. Now this is a trivial result, but it forms the basis of Cavalieri's method. Next, he proceeded to a more complex problem, finding the sum of the squares of the indivisibles of a triangle. In other words, he wanted to find x1 squared plus x2 squared plus x3 squared, and so on, which we can write for short as sum of x squared. To visualize his approach, let's first tilt the triangle inwards. Cavalieri placed a square on the first indivisible, a square on the second indivisible, and so on, effectively forming a pyramid. And Cavalieri arrived at the result that the sum of the squares of the indivisibles of a triangle is equal to the volume of a pyramid, which was long known to be 1/3 the base times the height. The base of the pyramid is this square, which is the base of the original triangle squared, and the height of the pyramid is this line, which is the height of the original triangle. And Cavalieri arrived at the result that the sum of the squares of the indivisibles of a triangle with a height and base a is equal to a cubed over 3. Now this result allowed Cavalieri to find areas and volumes of various shapes. Let's see how we can apply it to find the volume of a cone with a height and a radius a. Now according to Cavalieri, a cone, being a three-dimensional figure, is composed of indefinite number of indivisible planes, which are circles in this case. And the volume of the cone is the sum of the areas of these circles. To better visualize the approach, let's reduce the number of circles and shrink the cone to be able to spread them side by side. Now if we call the radius of the first circle r1, then its area would be pi r1 squared. If we call the radius of the second circle r2, then its area would be pi r2 squared, and so on. And as mentioned earlier, the volume of the cone is simply the sum of those areas. Now when we zoom in, we notice that the radii of the indivisible circles that consist the cone correspond to the indivisibles of a triangle, which we previously called x. So we can replace r1 with x1, r2 with x2, and so on. We factor pi out and write this expression more compactly as pi times the sum of x squared. But we already found that the sum of x squared is equal to a cubed over 3. And we arrive at the result that the volume of a cone with a height and radius a is equal to pi a cubed over 3. The result wasn't new. Archimedes found it almost 2000 years earlier. But the method was, or at least so Cavalieri thought. Encouraged by this result, he kept going forward. Next, he set out to find the sum of the cubes of the indivisibles of a triangle. And he found it to be equal to a to the power of 4 over 4. Now here Cavalieri noticed a pattern. The sum of x, which is x to the power of 1, is equal to a to the power of 2 over 2. The sum of x squared is equal to a to the power of 3 over 3. The sum of x cubed is equal to a to the power of 4 over 4. And he wondered whether this pattern continued. So he calculated the sums of the powers of x all the way up to 9, and observed that this pattern did indeed continue. So he boldly conjectured, without a proof, that this pattern holds for all values of n, where n is a positive integer. And although I'm getting ahead of myself, but if you're familiar with calculus, you'll notice that this formula is an early form of what we write today as the integral from 0 to a of x to the power of n dx is equal to a to the power of n plus 1 over n plus 1. A result that's central to calculus, particularly to Newton's work, as we will see later. Yet it was discovered, or at least conjectured, decades before the development of calculus. Just like Kepler before him, Cavalieri's work was widely read and vigorously criticized for its use of indivisibles. Yet again, he inspired many mathematicians to use indivisibles. But despite the successes of indivisibles, the landscape of mathematics was about to change forever with a groundbreaking invention, the Cartesian, or the XY plane, that opened the door for new integration methods, such as arithmetic quadratures, the fourth method on our list in the history of evolution of calculus. Up to this point, all the methods we studied were purely geometric in nature, relying on visual reasoning and spatial intuition. However, the XY plane allowed mathematicians to use the power of algebra in analyzing curves. Let's explore this by finding the area under the parabola from its vertex to a given point A. Now the XY plane allows us to represent the parabola as an equation, y equal x squared. And the main idea is to divide the region into rectangles, find the area of each rectangle, and then sum them up. Clearly, we have errors, which are these bits here. However, the more rectangles we use, the smaller the errors get. And when the number of rectangles go to infinity, the errors go to 0. Let's start with 5 rectangles and see if we can uncover any pattern. The width of the first rectangle is a over 5, since we divided the region into 5 rectangles with the same width. In fact, the width of all rectangles is a over 5. The height of the first rectangle is this point, which is x to the power of 2. And x in this case is the width of the first rectangle. Therefore, its height is a over 5 all squared, or a squared over 5 squared. And its area is the width times the height, which is equal to a cube over 5 cube. The height of the second rectangle is this point, which again is x squared. However, x in this case is the width of the first 2 rectangles, a over 5 plus a over 5. Therefore, the height of the second rectangle is 2a over 5 all squared, or 2 squared times a squared over 5 squared. And its area is 2 squared times a cube over 5 cubed. We can continue the same way for rectangles 3, 4, and 5. Now the area of the entire shape is the sum of the areas of the individual rectangles. We factor a cube over 5 cube out, and we're left with this simple equation. Now to improve the accuracy of our calculation, we increase the number of rectangles, let's say to 6. And rather than repeating the entire process, we simply replace 5 with 6 and add 6 squared to our sequence. Continuing the same way, for k rectangles, we get the following formula. Now this sequence is known as the sum of squares, and it was long known to equal k into k plus 1 into 2k plus 1 over 6, where k is the final term in the sequence. In our case, it's the number of rectangles we chose. After basic simplification, we get the following formula. Now the bigger the k, which is the bigger the number of rectangles we use, the smaller these two terms get. And when k goes to infinity, these terms go to 0. And we get that the area of a parabola from its vertex to a given point A is equal to a cube over 3. We can write this in modern terms as the integral from 0 to a of x squared dx is equal to a cube over 3. The same result that Cavalieri arrived at geometrically. However, we did so algebraically or arithmetically. Using a similar approach, Pierre de Fermat was able to prove Cavalieri's conjecture. By this stage, mathematicians studied and analyzed many different curves. Yet there was no unified method to analyze all curves, and no one expected that such a method existed. Each curve required its own unique approach, and mathematicians used to challenge each other to find areas and volumes of various shapes. But then came a discovery that changed everything. A discovery that could be considered one of the biggest aha moments in the history of mathematics. A discovery that gave birth to calculus, and therefore it wouldn't be an exaggeration to say that it changed the course of history. It is the discovery that the method of finding areas and volumes is nothing but the inverse of a much easier process: the method of finding tangents. To understand how this revolutionary link between areas and tangents was discovered, we must first explore the pre-calculus methods of finding tangents, which is the topic of our next video. See you then.